Thank you for joining me here. Today I am here to present design of multiband antenna with rectangular and circular slots for 5G mobile technology. I am Pratiksha Dage presenting this with Shraddha Doke, Dakshata Chiman, Megha Chauhan and under the guidance of Professor Naresh Kumar Joshi sir. Let's move towards abstract. Nowadays, due to rapid growth in mobile users, the request for mobile communication has been raised and users need more features like high data rate, good communication and reduced traffic on their mobile phones. And all these requirements can be met by 5G technology. 5G operates from 24 GHz to 86 GHz at millimeter wave frequencies. We have used a microstrip patch antenna and Zealand IE3D software for modeling and simulating the antenna. All the simulated results are presented at frequencies 26.1 GHz, 45.98 GHz and 58.86 GHz. We are moving towards 5G because there are some limitations in the 4G technology like poor quality and coverage, connection loss, high energy consumption, bad interconnectivity, overcrowded channels, co-channel interference, which will not satisfy the recent demand. Introduction. For designing an antenna, we consider parameters like resonating frequency, antenna size, manufacturing cost, and bandwidth. And all these meet the future demand like good coverage, low cost, best quality of service than the previous versions, high connectivity, speed and capacity, low cost per bit, less data traffic, and many more other demands. One more advantage is 5G mobile phones will provide high resolution to the users and lead to the evolution of decrease in mobile phone dimensions. Microstrip patch antenna. Our microstrip patch antennas consist of three parts, that is patch, substrate and ground plane. It provides us various advantages like low cost, small dimensions, lightweight and easy to manufacture and fabricate. We have chosen Rogers RT5880 substrate which is the best for wave. The methodology followed for our project is first we have selected the application frequency and based on this we have designed our parameters. After that we selected our substrate. Then we designed the schematic of antenna in IE3D software. Based on that we have designed our layout. Then we did our simulation and at last we plotted our parametric variations with respect to frequency. Design calculations. Our project's dimensions are calculated on by using these several basic equations which are listed here. First, to find patch width W is equals to C upon 2 into Fr into root of 2 upon epsilon R plus 1. Here Fr is the resonating frequency which is 26 GHz. To find effective dielectric constant epsilon R effective is equals to epsilon R plus 1 divided by 2 plus epsilon R minus 1 divided by 2 into 1 plus 12 into h by 12 whole raised to minus half. Next is effective length, that is L effective is equals to C upon 2 into Fr into root of epsilon R effective. Fringing length, that is denoted by delta L, which is equals to 0.412 into h into epsilon R effective plus 0.3 divided by epsilon R effective minus 0.258 into W by H plus 0.264 divided by W by H plus 0.8. Next is actual length, that is L is equals to L effective minus 2 into fringing length. Next is width and length of the ground which are calculated as 6h plus W and 6h plus L respectively. Antenna geometry. Our antenna is as shown in the picture and this geometry consists of copper ground or Rogers RT580 dielectric substrate with permittivity of 2.2 and height 0.508 mm. The microstrip antenna proposed has a low profile structures dimensions like 3.56 mm into 4.56 mm into 0.508 mm. The antenna is designed and simulated on Zealand IE3D software for calculating return loss, radiation pattern, gain, and antenna dimensions. Here we have listed our dimensions for required parameters. Now let's move towards the simulated result. First is return loss part. It is a return loss is a measure of reflection from an antenna which is represented by S11 and also called as a S parameter. It is always better to have return loss in negative values, which shows that the losses are minimum during the transmission. For 26.1 GHz, we have got minus 31.70 dB return loss. For 45.98 GHz, we have got minus 23.089 dB, and for 58.86 GHz, we have got minus 12.53 dB return loss. Next is bandwidth. The bandwidth of antenna refers to the range of frequencies over which the antenna can operate correctly. Bandwidth for 26.1 GHz is 3.36 GHz, and for 45.98 GHz and 58.86 GHz it is 3.9 GHz and 2.54 GHz respectively. Gain plot. It is defined as how far the signal can travel through the distance, and it is always better to have more than 3 dB gain. For 26.1 GHz, we have got 4.18 dB gain. For 45.98 and 58.86 GHz, we have got 5.33 and 6.30 dB respectively. Radiation pattern. It is the graphical representation of the energy radiated by an antenna. The energy radiated by antenna is represented by the radiation pattern of the antenna. This is our radiation pattern in E plane for phi is equals to 0 degree and phi is equals to 90 degree. This is the 3D structure of our radiation pattern. Last, I will like to conclude my presentation with our results. That is, for resonating frequency 26.1 GHz, return loss is minus 31.70 dB, gain is 4.18 dB, and bandwidth is 3.36 GHz. For 45.98 GHz, return loss is minus 23.89 dB, gain is 5.33 dB, and bandwidth is 3.92. And last, for 58.86 GHz, return loss is minus 12.53 dB, gain is 6.30 dB, and bandwidth is 2.54 GHz. Thank you.